Like maybe cutting an apple pie. Don't laugh at those things.
Just stay away from it. Just stay away from the door. That's why I came.
That's not.
Yeah.
Nobody emailed Matt saying they found.
Do we just not have any interest?
I mean,
I know you guys are.
and like all of you guys came that didn't organize this. That's interest.
I'm not interested in this. Wes is my right.
One of these days we want to.
You better show interest.
Are you?
I just want to stop attending ACM after yesterday's meeting.
Yeah. We're about to have a
Yesterday's meeting,
I was like,
who put on a horrible meeting that made Jacob not wake up? Wait.
Yes, it was me. It was I. You have been bamboozled. 'Twas all illusions.
Bad food. I mean, good food, but bad.
There are snacks over there. Yeah. Please feel free to partake. If you're interested in accessing our notes for tonight's event, you can access them using this short link. I highly recommend it. Sam and I, we both put in a lot of like links and stuff to like extra resources. Because while today, like the goal of today is to provide an introduction, there's no way that can be comprehensive, and there's so much more to learn, and we wanted to kind of set you free into this wide open world of cryptography.
Additionally, all of our instructions are encrypted, so that we're helping you with your first step.
They're encrypted in the wonderful language that is English. A Caesar cipher.
That's hard.
I know.
Yeah.
Everything's encrypted, but don't worry. It's with a Caesar cipher. The key is Z. It's fine. Yeah. Do I do the jokes?
It's
You
the
can do the
Caesar
jokes.
cipher with
You got
a
the jokes.
displacement of 0.
We're doubly
26.
applying ROT 13. Don't worry. This stuff will make sense to you today. That's
all
kind of the
separated
point.
by a common language.
So our notes right here. Highly recommend you take a look. Yeah. So cryptography is a fun and interesting subject. We're excited to be bringing this to you. My name is Ben Myers. I'm the president of the Association for Computing Machinery, which is our computer science club. This is Sam. Sam, do you want to introduce yourself?
Samuel Jackson, president of the mathematics club here on campus. You may have seen me in the movies. It's fun.
Oh my gosh, it's really him!
I do autographs afterwards, so please hold your applause.
Excellent.
That would be true.
Yes, cryptography. It's a really fun subject. There's one anecdote that Sam and we really love. It's about Queen Semiramis. Semiramis was an Egyptian queen, and she devoted her life to codes. She was super fascinated by codes and ciphers and all this fun stuff. And, I mean, she died. She was an ancient Egyptian queen. Ancient people tend to die. But her tomb was found many, many years later. And supposedly, anecdotally, there's not many attestations of this. But supposedly, like, after people went through, like, code after code on her tomb, like, the final message was basically, like, you're wasting your life with this. I forget what the exact quote was, but it's a pretty golden story.
Yeah, so she had a message on her tomb that was like, rest here, solve these ciphers, eternal riches, all sorts of awesome stuff. And then nobody could do it until one day somebody, went through all these ciphers, reached the last one. It was just like, you terrible person, I'm dead. Why are you in my tomb? Like, there's nothing here. If you had studied something more useful than cryptography, you wouldn't be in like the middle of a tomb right now.
It is honestly incredible. And I wish we could find like more people attesting to this. Like it's just kind of like one person's like anecdote, but it's beautiful, and I choose to believe it's true. So therefore, it is law. Yeah, absolutely. So cryptography is such a big subject. we wanted to start with really one of the most basic ciphers out there, and that's the Caesar cipher. This is probably one that you've done before. I think you actually have to do it for Computer Science 1. But we wanted to start with this because it gives us a very useful base for defining terminology that is going to be very, very present throughout this entire presentation. So the Caesar cipher is pretty simple. You have some numerical offset. You apply it to a string, right? So say your offset is 3, which is apparently what Julius Caesar used. He used the offset 3. So A's became D's, and B's became E's, and so forth. This is starting to look a lot like my academic transcript. Oh. That one wasn't planned, by the way.
That was actually. It took me a sec, but I got it.
But it's really, really simple. And in fact, I have a nice demonstration that I made because this is fun, right? And of course, you can't see it because projector. Actually, can we turn off the lights? That would be great. So yeah, the link to this is available in the notes, but on this site, you can decide what your key is, right? You can even have negative keys, right? You can type in some plain text. Plain text is just stuff, it's strings waiting to be encoded, right? Waiting to be encrypted. So we've got our plain text, we've got our key, that key is the offset, right? We can hit encrypt, and whoa, magic happens. So hello becomes lips. And we can go the other way around. Let's say I had hello here. I wanted to go, you know, say key 8, right? We can hit decrypt, and apparently our original text was ZWDDG. Very meaningful. I hear it's German. Yeah, so this, though, it's maybe fun as a computational problem, but it's not terribly interesting. It's very insecure. What are some security issues that you might see with something like this? Yes, Wes?
It's vulnerable to frequency analysis.
Very good, right? So the issue is, like, as we can see from this wonderful table here, like, every letter always becomes the same letter under the system. And this is a problem because, like, in English, E is so common. It is the most common letter by far. So if you have a sufficiently long text encrypted by a Caesar cipher, all you have to do is determine which letter is the most common, and most likely that's E. But even, like, you don't even have to worry about that because there are so few keys available. If you think about it, right, the keys map to, like, the numbers of, like, 0 through 25, right? Even if you have some big key like 42, well, that's going to become it's going to become whatever 42 mod 26 is. So there are so few keys that you could reasonably do a brute force. Like, you get 25 different options, and you just look at this and go, I can read that one. There you go, right? Like, congrats, you've cracked the code. It's not a very secure code, but it's a very useful starting ground for helping us understand some very, very crucial aspects of cryptography. We talked about plain text. Cipher is encrypted plain text, or it's our message that's been encrypted. We have a key, that's the value that we're using to do our encrypting. And also one thing is the key space. The key space is the set of all possible keys. And we want this to be massive, right? We want there to be so many possible keys that there's no way you could reasonably expect to test all of them. Yeah, so kind of went through some of these, but yeah, so how many of you guys are programmers, or at least CS? All of you guys. All right, so what would an encryption function look like for you guys? If you were given like a string of plain text and a key, what function might you write to actually do the encryption?
I can answer, but I want someone else to talk.
You can answer. That's
Throw it
fine.
through XOR.
You what?
Throw it through XOR.
XOR, you may be able to do XOR. I don't actually know.
Actually, yeah, so that's the general idea of what we want to be doing. So, well, kind of. We want to be adding things together in this.
Or subtracting.
Or subtracting, yeah.
But
Same,
that's just negative addition.
yeah, same thing kind of. So we've got a key, we've got some letter. What do we want to do? Well, we want to just add, the two together, we get a ciphertext.
Mm. Yeah, so encryption, decryption, not very hard, right? If you've got some key, for simplicity's sake, let's say like our internal representation of the alphabet just goes ahead and starts A at 0. That's not actually the case, but it's a simple fix. But you could just add whatever your key is to the current character. So we're starting with like H, right? Hello world starts with H, and our key is 3. We do H plus 3, we get K. We get K. And we can also, though, use modulus, right? So that's for when we reach past the end of the alphabet, we would use the modulus function. So we would just take whatever our result is, do mod 26, and it's whatever letter is there. That's actually going to be our plaintext. And that leads us really nicely into a brief discussion on modular arithmetic. This will be very relevant later. So modular arithmetic. In a mod n arithmetic system, one will count from 0 inclusively to n exclusively. Upon reaching n, the system wraps around and begins counting at 0 again. This is much like a clock, right? Although clocks go 1 to 12, but we could have like the 24-hour counting system that actually goes 0, 1, 2, 3, all the way up to 23. And then it wraps back around to 0. So those are the only numbers that can exist in that system. In a mod 24 system, you only have access to the numbers 0 through 23. A bit of notation that's going to be associated with this. In CS, we're used to writing x mod n, and mod is a function here that returns the remainder of x divided by n. However, this workshop is going to be using the mathematical notation. So we say x, there's that like triple equal sign, that means it's congruent. X is congruent to a mod n, means in a mod n system, x is going to map to a. In other words, the remainder of x divided by n is a. So we're saying, yeah, these things are equivalent in our modular arithmetic system. So 3 is congruent to 3 mod 5, because the remainder of 3 divided by 5 is 3. But 10 is congruent to 0 mod 5, because the remainder of 10 divided by 5 is 0, and so forth. We have -1 is congruent to 6 mod 7, or we could say that 3 is congruent to 0 mod 3, for instance. Yeah, does that make sense to everyone? Any questions about modular arithmetic? Are you saying no, it doesn't make sense to you?
Makes sense.
Okay, good. Just wanted to make sure. Yeah, so there are a couple of examples here, but I already kind of did the demo. If you have access to the link, you can go ahead and give this a try. But I did ask, like, how it... Yes.
One question, sorry to interrupt.
Absolutely.
You said that 3 mod 5 is 3, which makes sense.
Yes.
Then 6 mod 7 is -1. In that, so
So
in
now-
that way, 3 mod 5 can also be -2, isn't it?
Yes.
Yeah.
That's exactly right.
So, but like any mathematical operator for now, we should have some unique key, right? Because in the end, it's like a particular number is getting associated with like 2 possible values. So will that be okay, or like that's expected?
Yeah, so actually in this case, you're exactly right. So 3 mod 5 is going to be the same as -2 mod 5. There's also 8 mod 5.
Right.
And so actually, mathematically in modular arithmetic, we're sort of working with this giant big set. So that's everything 3 plus 5 is 8, so that would be there, 13. So everything's in there.
Okay.
And then normally we just denote it using 0, 1, 2,
Okay.
sort of the least thing.
Right.
Yeah, so it looks like what we would expect a computer to spit out mod n. Mathematically, it's sort of this big set, but normally we can forget about that.
Yeah, so I already did kind of ask you a couple questions about, like, is this secure or not? The answer is no, it's very not secure. There are minor variations you can use. A particularly famous one is the Vignere cipher. The Vignere cipher is where you use a word instead of a number as your key. So, for instance, if you were to encrypt the word cryptography using the key, then you would do C plus K is M, R plus E is V, Y plus Y is W, and so forth all the way down. And you end up getting
Your vocabulary
That's probably-
is fantastic today.
Thank you. That's probably Swedish. Yeah, so Vignere, though, it turns out pretty easy to crack as well. I really want to give you a nice demo of that. So in this repository, I will show you. Oh, as I don't want to go the full. Just want to go to crypto. Actually, no, I'm already here. Cool. So in this repository, you'll see I have this CCGRX and CCGRX analysis.
Sorry.
So, yeah, I found the entire text of Alice in Wonderland on Project Gutenberg, and I fed it through a Vignere cipher. And as you can see, like, here it is, right? It's all this, lots of stuff, right? It's like, how would we even begin to tackle this? How would you guys start? What would you do? This encrypted with a Vignere cipher. You don't know what the key is that's been used.
Frequency analysis first.
You-
Frequency analysis of the letters first. Because there are
You can do analysis on the letters. I would say that probably wouldn't be super helpful for you, because if you have like a key of n letters, right? Well, each letter is going to, like, if you have a sufficiently large plain text, each letter is going to fall on each character of the key, if that makes sense. Letter frequency analysis isn't very helpful.
you're looking for 2-letter words.
Yeah, there you go. Now you're doing word frequency analysis. So I fed that entire text through a word frequency analysis tool, and I found some interesting trends. So one thing that you'll notice is there are a bunch of 3-letter words here, right? Well, if we can assume that the original text is English, what might those 3-letter words be?
And
The is the big one, right? So, yeah. So you can do, let's see, the top one I believe was KFT. So KFT is our cipher. We can assume it's the decrypt. Well, okay, so it's implying that RYP is at least part of our cipher. But we can do, here we go. KHT is another one. So RAP might be part of our cipher. Let's see, we've got VYC, CRY. So we had an RYP and we have a CRY. We might assume that those are like, that the RY is the same RY there. So maybe we have CRYP. You can keep doing this. I do encourage you to. I've got that stuff in the repository. You'll figure out pretty quickly what the cipher is if you do that. And in fact, it's really cool how, like, mathematically, ideally, this works. Because I had a 12-letter key. And what I found was, in the original text, the appeared 6% of the words. So 6% divided by 12, that gives you 0.5%. And if you look at all, like, the top 3-letter words, you'll find that they're about 0.5%. So it was really cool watching that happen. But I've gone way too long about this stuff, so I'm going to pass this off to Sam. Sam's going to talk about this beast. Here you go.
Yeah.
Yeah.
So.
Oh, do you want me to?
I mean, either or, it'll be fine. So, we had Caesar Cipher, we had Vignere Cipher. Lots of stuff happens. We can just ignore that. World War II. How many of you have heard of the Enigma Machine? Great. Everybody. Yes, we all love the Enigma Machine. Who knows how the Enigma Machine works? Great. This won't be a waste of your time then, hopefully. So, this is the Enigma Machine. Can we zoom out?
Yes.
At all? Possibly.
Yes, we can. Does
Awesome.
that help?
Yeah.
I'll go for this.
So, Enigma Machine, used by the Germans in World War II. One of the, first mechanical sort of crypto systems. Terribly complex. You've all probably heard the story. It took forever to break it. That's why we won, perhaps. If you're a crypto buff, that's definitely why we won. If you know your other history buffs, maybe other reasons. But, so, this is what it looks like. You see it has a keyboard of letters. The operators would press the letters. It would go through its magic encryption. And one of these light bulbs would light up. And that actually signifies to what the cipher letter is. So if you scroll down just a little bit and click on that YouTube link, this is a working Enigma machine that somebody took a video of at the National Cryptologic Museum, I believe. It's kind of poor quality, but you can see he's pressing letters and something's lighting up there. So the U lit up there, and if we go through that again.
Yeah.
Yeah, so you see, press the C, and the X lit up. Press the D, the Z lit up. And you'll also notice that the rotor at the top clicks. One more time.
Sure.
Yeah. The rotor at the top moves once every time. And so these rotors are actually what gave the Enigma, that's what made it such a pain to solve. So if we can go back.
Go back to the notes?
Yeah.
Cool. Can do.
Thanks.
Nope, that's the wrong notes. Notes!
Yes. So it has three rotors. The Enigma has three rotors. It ends up right, middle, left, and then a reflector. So this is an idealization of what is happening on the inside of the Enigma. So the operator starts, he presses a letter, and then each one of the rotors is actually just wiring connecting two different letters together, for lack of a better word. But essentially what it does, each rotor is unique. You press the A, an electrical current gets sent through the circuits. It goes through each of the rotors, following a path. It hits a reflector, which just bounces the current back. It comes back through all three rotors, and then a letter lights up. The rotor then clicks forward once, as this lovely diagram shows. And so now we press A again, and we get a different number, a C.
Sam, that's a letter.
Do what?
That's a letter.
You're a computer scientist, they're the same thing.
Did I say number? It's fine. I'm used to numbers. It's all good.
Simply a representation of a number.
Yeah, we'll go with that. Alright, great. So, who wants to do arts and crafts? Because I have paper enigmas. We're going to make our own enigmas. Is anyone excited? Yes. 2 thumbs up. Great.
I can't give you 2 thumbs up, but...
I'll take what I can get. So, I have 3 pairs of scissors and 2 things of tape. So we will share. I apologize. But All of these things. There you go. Yeah, so what we're going to do on here is the top part instructions, you know, whatever. Just cut along all the dotted lines. Those of you who happen to have scissors, again, I apologize. I could find 3 in my house this morning, which I was pretty happy about. That was 2 more than I was afraid I was going to find.
I'm just gonna write the paper.
Alright. You should throw it at me whenever I say something wrong. One other pair of scissors. Yeah. Yeah. Yep. We got crushed in my backpack just a little bit.
Does it not turn? No.
It does, so these are actually separate pieces of paper. So.
Oh, I see. Oh, gotcha. Okay.
Yeah.
Cool.
Yeah, it's also on there kind of awkwardly, so I apologize. Turns out I made the middle tube slightly too big, so I just had to tape the others around it.
Gotcha. Do you want to go ahead and
I mean,
up to you?
I prefer to take a couple minutes. Yeah.
See if for streaming purposes, at least.
Sound
Yeah,
by the way.
it's working.
Well, at the very least, we have an interesting visual.
It's a one-eyed sad face.
Maybe like say on the stream what we're doing right now, so people don't, like if somebody's watching, they don't think.
So
Stop
there,
randomly.
hopefully there should be a link in here. This is what I'm trying, but it doesn't seem to be working. But we're doing arts and crafts right now. We're making our own enigmas. Please, DIY. Do this at home. It's fun stuff. Yeah.
Yeah.
Because I think part of it is like the Enigma, when you just see it as like rotors turning, it can be hard to visualize exactly what's happening. But when seeing something like this set up with all the wiring, right, made clear, it can be very easy to trace the path and go, oh, okay, that's how it's working.
Yeah, these nice people have taken the top of the line cryptography of World War II, printed it out on paper, it's in your hands.
Yeah, but the story of this is really like fascinating. Every month, German officers, I guess, were given a sheet of like every day, this is the exact configuration we want you to start off with. And that's a really big deal. Because like there were 5 different rotors and you had to choose 3 of them. And so you were given this like code sheet that's like, on the 1st of this month, you're going to use this initial configuration, and on the 2nd of this month, you're going to use this one. And so that's how Germans knew like how to start, like what to start on. But the issue is like, what happens if you lose the code sheet? Like, what happens if those nasty Americans or Brits get their paws on the code sheet? The sheets were printed with like a soluble ink that like if you were to pour water on the document, like the ink would vanish. Which is like, it's kind of cool.
I didn't know that actually, that's really nice.
Yeah. But there are so many like initial configurations. What was the number? It's up here, but it's like,
yeah.
It's absurd. It's like, I think that's 150 trillion. 150 trillion ways pairs of letters can be interchanged, and that's impossible to do brute force.
So how is this a German machine if it doesn't have umlauts?
Well, I mean,
Or is this just a remake for the English alphabet?
I have heard that question before, and I don't remember. I think they just ignored umlauts. but I don't actually remember.
Okay.
So, the Enigma Machine in the video was an original Enigma Machine, and it does have that standard American-looking alphabet on there.
Okay.
So I don't actually remember.
Maybe they knew the Americans were better.
I
So they just
mean,
used their alphabet.
I don't think that would be it. They seem pretty pro-Germany, but
To a fault, you might say.
maybe just a little bit.
Well, I know that the system the Americans used, not during World War II, but starting in the 60s, used a 5-bit Modoc code. And I was an operator in that system. And we just, we needed to send, like say, fiance, we would send that in a military message. You just ignore the accent on the key.
Okay.
It's, as long as the meaning is clear.
I will point out that it is slightly easier to actually wrap the rotors around. I taped mine together, tried to fit it on, then I was like, no, and undid it. We have
scissors.
Yeah, and also when you're attaching them, go ahead and attach the third rotor so that it's closest to the reflector, and the first rotor so that it's on the outside edge where the alphabet is. So it'll be 1, 2, 3 going in towards the reflector.
Okay. Actually, this. Where are you guys at on this? Are you in a good state? Like,
No, not yet.
I need tape.
Yeah, there are only 2 rolls of tape. They should be around somewhere.
They are going around. Okay, that's on the back.
I mean, you're sitting in the back being antisocial. That's why they haven't reached you yet.
I know. Great.
Yeah. Gotcha.
got me down?
No.
I'm one of the cool kids.
Just this time.
I'm really bad with watching graph.
Next time, this time, yes.
Wait, are we not supposed to actually notch it?
No. No, so the notch actually is how the rotors. I mean, it's fine if you did. Yeah. So whenever the notch flips all the way back around, that's when the second rotor moves. So the first rotor will go around 26 times, then it'll flip, the second rotor will start going around.
Mm-hmm.
When that goes around 26 times, the third rotor will move once. And,
I see.
yeah.
And it's like the hour, minute, seconds hand.
Yeah. But cooler, because there are 26 of them. Do you have one working Enigma machine? Woo!
Well, I don't know if it's working. Assuming it works.
I mean, it looks like it works.
You done with it?
We'll go through it in just a
All right,
second.
who's ready to make the third round?
Gracias.
Yeah, so if you do have the rotors, go ahead and slide them on. With rotor 3, so you'll want the rotor 3 to be closest to this side.
Okay.
So this will be sort of the front, and this will be the reflector that ends up going on. Yeah. Yeah, it's a little awkward. The tube, I think, is slightly too big for the actual rotors. What these fine ones.
I was thinking,
Yeah. If you guys are having trouble sliding the rotors on, just go ahead and untape them and then wrap it around before you actually take the rotors close. Yeah, well, I know that after.
Void.
Yeah.
I just assumed it was Jacob.
Use the void?
huh?
Are you the boy?
What are you talking about?
Chat.
No, I'm not.
I'm not watching the lecture. Why
What
would I
is
be the
red
boy?
lecture?
I don't know.
That's Wes.
I mean, you're sure as hell aren't the man.
Whoa.
I'm
Ooh.
The
Oh.
lecture.
Yeah, that's Wes.
Alright, at least talk about breaking it, at least.
I mean, I like to go through. Oh, well. Alright, raise your hand if you have not finished yet.
I haven't even started.
Okay, well,
I don't go to school here.
You can go. You can go ahead though.
okay. Well, so what we end up doing, so to simulate the Enigma, essentially you'll turn the rotors however you want to start. So I have mine so that the sort of the label rotor X is right above the line that I actually taped it on. So on the first rotor, if I follow the A line, that looks like it connects to the E on the first rotor. On the second rotor, it looks like the top line is going from A to A, and the third one is A to B, which is just how this configuration is set up. Yeah. And then to encrypt something, all you have to do is choose a letter on the side and follow the wire all the way across.
Can you put a link to where you found this like worksheet?
Yes, if you scroll up.
What is this?
So no,
Oh.
just right now.
Oh,
So yeah, this is the paper Enigma. There is another one if you Google paper Enigma. It's bigger and you actually wrap it around a Pringles can, so it might work better. But for our purposes, this is smaller. You don't need whole Pringles can. I can't eat that many Pringles.
What? I believe in you.
I mean, I see. We should have coordinated. You could have brought Pringles as snacks. That would have been the
Look, everyone finish the snacks so that we can continue the program.
It's fine if there are snacks in them. Not only is it a world-class encryption scheme, it's also dinner. That's the pinnacle of human achievement right there.
Right there, yes.
That or if everybody's gone, we can get toilet paper bowls, buy toilet paper in the hall.
Yeah, but somehow that seems like not something I want to do in like a kind of professional environment. So I'm gonna go with the Pringles cans.
Yeah, we could do it like human sciences.
True, we don't care about that building as much, so you know. But you didn't hear me say it. Neither did you two. Nope. Nobody heard that. So, paper enigmas. We can come back to this later afterwards if you have questions. But I do really quick want to mention breaking the enigma. You know, if you look at this wiring scheme, you know, physically, it's going to be impossible for something to come back to itself. Because, I mean, if you're pressing a wire, it can't map back to itself because then you won't get any output. That's one of the main mathematical flaws that people point out. But it actually turns out there are a lot of other flaws just in how it was used. So, I mean, if I captured a code book, well, great, I know what the codes are. There are common rotor settings, the really simple ones. I'm just going to choose, you know, set rotors 1, 2, 3, all to position 1. Like, it's simple, nothing complicated. There are also common phrases. So, you know, if I know the statement ends in Hail Hitler, well, then I know that the last letters have to be, you know, exactly in that order.
Also, you joke, but that was a legitimate security issue. All of the Germans ended their messages with Hail Hitler. And that was, like, tremendously insecure. But that was, like, actually a thing.
Yeah, and I also want to point out something kind of interesting. So the Germans weren't just using the Enigma. I mean, they had several ciphers. They were talking to the Italians, all their allies, whatnot. And so, you know, the allies broke some of those. And so if I received a message on one of the broken ciphers and then sent it out using the Enigma, well, that's also bad because now I have what's probably the plain text. It's pretty identical. And I've got the ciphertext, so now I have a better chance of solving what rotor settings there are. And so there's a nice comic up here. which is that, mathematically you want to say, great, I'm going to use, 1,000-bit, 5,000-bit AES. NSA is going to take, 20 lifetimes to crack this. Nothing's going to happen to me. And, as the comic says, well, what actually is going to happen is that, if you tell someone the password, well, someone hands you the key to something, then it's broken. And that's going to be far easier to actually break these things than trying to find what the key is. And so, we're going to move on to our third topic this evening, which is diffie-hellman key exchange. So we talked about Caesar cipher, we talked about Vignere cipher, we talked about the Enigma machine. All three of these assume that we both know what the key is. I've talked to you beforehand, and I said, great, we're going to use a key of 5. It's going to be the best key. It is perfect. No one's going to know. But what happens if I want to talk to Ben? I've never met Ben before in my life. I have no way of communicating with him because the aliens are spying on me every moment. It happens, man. Don't laugh. So how are we going to do that? So there are these nice people, Mr. Diffie and Mr. Hellman, which figured out how to be able to exchange the key over an untrusted medium without letting any eavesdroppers be able to know what it is. And so we're going to start off back to a little bit of math. If I told you, so modular arithmetic, we're all fairly familiar with how it works, and stop me at any point if you're uncomfortable with what I'm saying. You don't believe me. Nobody should believe me. People should believe the math. So I want to tell you that, sure, whiteboard. It's a flaw of mathematicians. So we're going to take a different whiteboard marker. And maybe we won't do this. Okay, great, there we go. So let's take some prime P, and we're going to choose a G. So both of these are going to be integers, so 0, 1, minus 1, but it's a prime, so that's going to be positive. And so I'm going to tell you that we can compute G to the A mod P, that we have an efficient algorithm to calculate this for any A. Does anyone believe me? Does anyone not believe me? Does anyone have anything to comment about this statement?
Yes, this is what banks use online.
Say again? So no, actually, so that's related, but in this case, we actually have a different algorithm. So I have an example up there. So if we have, let's choose our prime to be 67. G is going to be 7 because why not? It's a lucky number. And A is going to be 28. And so we want to find what 7 to the 28th power is mod 67. And so we're going to do this by repeatedly squaring G. So we're going to take G times G, so G squared comes out to 7 times 7, that's 49. Well, that's just 49 mod 67. G to the 4th comes out to G squared times G squared. We know that's 49 times 49. That happens to come out to be 56 mod 67. Now when we calculate G to the 4th, or G to the 8th, excuse me, we're going to take G to the 4th times G to the 4th. Well, we know that G to the 4th is 56. So, well, we're just squaring 56 then. So we calculate 56 times 56. That comes out to this nice big number, which is actually 54 mod 67. And we'll do that one more time. We'll get G to the 16. And then it actually turns out, well, what's 28? Well, 28 is just 16 plus 8 plus 4. And when we multiply exponents, we can just add them. So now G to the 28th is just g to the 16th times g to the 8th times g to the 4th. That turns out to be 47.
Mod 67.
Yes, thank you.
Yeah.
And so this is nice because, you know, if I'm raising something to the 28th power, you would think that I need to multiply it 28 times. I'm going to take g times g times g, so on and so forth. Hopefully you don't mess something up in the middle. And you reach the end. Well, with this, now we only need to calculate to the log base 2 of n. That's the number of multiplications we need to do. So we actually, it's not linear, it's logarithmic. That's great, we love logarithmic. Does anyone have questions about this? Does anyone want to flat out say I'm a liar? Yes.
So essentially what you've done is you just try to divide 28 into the powers of 2 and sum them.
Yes.
Isn't it?
Yes.
That's what we are trying to do. Is distributing the index of g.
Yeah, so it actually...
But what is the benefit we get out of this?
So the benefit is that sort of intuitively, if I'm trying to raise, x to the third, I'm going to multiply x times x to get x squared.
Right.
Then I'm going to multiply by x again. And so x to the fourth, I'm going to take x times x, x squared. Then I'm going to multiply by x again, which is actually a waste.
Okay. So basically what we are trying to do is utilize polynomials, the fact that it grows really fast, compute higher operations.
A bit, yeah. And we're also sort of abusing the sort of base 2 representation of whatever A we're using. And so with this, we can efficiently calculate g to the a mod p for really big numbers. Thousands of digits. It's not, we don't want to do that. Not by hand, at least. Yep, see? So, we're going to talk about the Diffie-Hellman key exchange now. So, we have 3 parties, and if you read cryptography books, these are probably the 3 parties you're going to see. You have 2 people who want to talk to each other, Alice and Bob, and you have some malicious eavesdropper, who is named Eve, coincidentally, who is listening in on their communication. She hears everything that goes between Alice and Bob. And so what are we going to do? And go ahead and scroll down to that, yes. So they're going to start, Alice and Bob are going to decide on a number g, and a prime p. Right? So it's kind of like what we were doing. We decided p, we decided g. And Eve can know that. That's fine. And what's going to happen next is Alice and Bob are each going to choose a secret number. So Alice is going to choose a number A that only she knows. And Bob is going to choose some number B that only he knows. And both of them are going to calculate g raised to that power of the secret number, mod p. So Alice is going to calculate g to the a mod p, and Bob is going to calculate g to the b mod p. And then they're going to exchange what that is. So now everybody knows g to the a mod p and g to the b mod p, because Bob sent Alice g to the b mod p, Alice sent Bob g to the a mod p, and Eve is in the middle and knows everything. And what Alice and Bob are going to do actually is say, well, Alice has g to the b, well, let's raise that to the 8th power. And that comes out to be g to the ab mod p, because you have an exponent, you multiply them, g to the ab. Bob also, now that he knows g to the a mod p, can raise g to the a to the bth power, get g to the ab mod p, and we're done. That's our secret key. Eve, sitting in the middle, knows g to the a mod p and g to the b mod p, but she can't do anything with that. That's a hard problem, classically speaking. And yeah. Does anyone want to say I'm lying? I'm giving you lots of opportunities. Does everyone believe me?
So why can't Eve?
So Eve does not know A or B.
Oh, she just knows.
Only Alice knows. Yeah.
Yeah.
Okay, that makes sense.
Only Alice knows A. Only Bob knows B.
Okay.
And it's actually like kind of cool because this is really pretty. It feels like simple arithmetic, right? We're just raising powers, we're multiplying powers, and yeah, we get this really cool result out of it. And so I have an example here, which goes through numbers, and if you work it out, then you'll see it goes to 14. I'm not really going to walk through this though. I will mention that, so we know that Eve knows g to the a mod p and g to the b mod p. Well, how would she go about finding g to the ab mod p? Well, she'd need to find a or b. And so this problem, trying to find a from g to the a mod p, is known as the discrete logarithm problem, which is classically a very hard problem to solve. We don't think we can solve it using, the computers in front of us. It'll take way too long. But, cool fact, which Ben will talk about.
Yeah.
Go ahead.
Quantum. So yeah, we're gonna give an overview of quantum cryptography. Disclaimer on this: I'm not gonna try to get too deep into the quantum mechanics of this because that's stuff that scientists spend like their entire lives trying to understand. But yeah, quantum cryptography is coming, and it is going to wreck everything. As computer scientists, as mathematicians, we need to understand this fundamentally to keep us safe. So, we've talked a little bit about classically hard problems. Specifically, we talked about the discrete log problem, which is for diffie-hellman key exchange. Now, also one thing I want to specify, diffie-hellman is not an encryption scheme. It's just a way of transferring keys securely.
Yeah,
But,
so once we have that key, at least with most implementations, we'll end up switching off to a symmetric encryption scheme like AES, because normally it's faster. We have a shared key now. We can go use a faster algorithm.
Absolutely. There are a bunch of there are quite a few ways out there that we can do this key exchange, and ways of like even coming up with like what keys we're going to use. One of the most famous encryption schemes out there, RSA, which is also one of the most widely used, their method of key, like thinking about like what keys are even valid and how they come up with it, it relies on prime factorization. So the idea is we can get two really large primes, and we can multiply them together. Multiplication is easy. Multiplication is like always easy, classically. But if we have a really large number, it is incredibly difficult to find the prime factors of this. This is the prime factorization problem. And when I talk about really big numbers, I want to clarify, like RSA uses at most keys that are 4,096 bits. Now, if you do 2 to the 4,096, you actually get 10 to the 1,234th power. That is numbers that is more than 1,000 digits, which is mind-bogglingly large, right? And you're not, if you're given these 1,000-digit keys, you're not going to go, well, I need to find the prime factors of this. Is 2 a factor? No. Is 3 a factor? No. Is 5 a factor? No. Right? Like, that just will not work. With our current computation power, classically speaking at least, that would be like lifetime of the universe. And there are ways that we've developed like slightly more efficient methods. Right now, the biggest candidates are the general number field sieve, which is faster for integers greater than 10 to the 100th power. If you're less than that, then you're going to want to use what's called the quadratic sieve. I have linked those Wikipedia articles. The math there escapes me, but go ahead, give it a try. But yeah, like, we are talking about absurdly big numbers, and these, like, the product of two really large primes, like, the only factors of that product will be the 2 primes. So it's incredibly inefficient. So yeah, this is where quantum computing comes in. And quantum computing, like, anyone who's been near me all day has just heard me talk about, like, guys, quantum computing is so rad, because it really is. Quantum computing is really cool. So quantum computing gives us access to entirely new algorithms that drastically reduce the time needed to solve problems of, say, prime factorization or the discrete log problem by exploiting features of quantum mechanics, such as superposition and entanglement. Now, if you're like me, and like are vaguely curious about quantum stuff, you probably tried to look up like what the hell even is this quantum stuff. And personally, I've not been satisfied with the kind of pop quantum mechanics out there. I feel like they drastically oversimplify in ways, because the reality is just like so much cooler. So when we talk about quantum superposition, usually we'll talk about like, oh, it could be like, or at least most like primers about quantum computing, we'll talk about like, oh yeah, we can have values that are not just 0 and 1, but they're like somewhere in between, man, and they can be like all the things at once, and we can use that to like check every possible prime factor at the same time. Well, we can check every prime factor at the same time. That's called parallelism. That's kind of solved. All we need to do is just hook together a bunch of classical computers. So where this quantum stuff comes in is really, really cool, because we have like entirely new algorithms. We aren't just checking every number at the same time. Like, yeah, there's a representation in the quantum state for every like prime factor, say, but quantum stuff, quantum behavior is very wave-like. And that means you get access to all the wave stuff like constructive and destructive interference. So if it's been a while since you've had your physics class, constructive interference is when you can add like two waves together and you get bigger waves. Destructive interference is when you add like two waves together and you get like smaller waves. And so you can devise algorithms like Shor's algorithm is the most famous right now, that will specifically kind of reframe the problem so that probabilistically, numbers that are likely to be the factors will be amplified. They'll be constructed, whereas numbers that are probabilistically less likely to shake out to become the factor, those become destructive. They go away. They flatten. And so what you're left with is what is most likely the correct answer. It's still very probabilistic, but if we have a number, it's easy to go back to a classical computer and say, hey, is this a factor, right? All we need to do is divide. But so much faster. And so there are algorithms like this that'll take what in classical computing we would consider NP problems, non-polynomial problems, classically considered like hard problems. We can take that and move them into polynomial time, at least quantum speaking. This phenomenon is called the bounded error quantum polynomial runtime, or BQB. And it is terrifying, because that means that breaking our classical encryption systems is going to be a piece of cake, right? So, like, what does this mean? Does this just mean, like, everything's going to break?
Yep.
Well, I mean, everything that we have now is going to break, but there are a couple of saving graces. Also, I didn't really mention it, but if you're interested in, like, Shor's algorithm and, like, how these algorithms actually work, check out this link. It's a very helpful playlist. Just 3 videos. It's by PBS Infinite Series. But, yeah. So, all hope is not lost, though. Once the quantum apocalypse happens, we still have some options. Just as quantum computing destroys modern cryptography, it'll also provide new solutions. The most prominent that people will talk about, in fact, it's often synonymous with the phrase quantum cryptography, the most prominent is quantum key distribution. So we talked about diffie-hellman as a secure way to pass keys with each other, to share keys with someone you've never met before. Quantum key distribution is like that, but brought into the quantum sphere. I've linked to that. It's really cool. But yeah, this is really secure because thanks to the Heisenberg uncertainty principle and the no cloning theorem, it's impossible for Eve, in our example, to observe the keys that we're sharing without accidentally modifying them. And they can't just like accidentally modify it to read it and then send back an exact copy because of the no cloning theorem. So if an eavesdropper tries to read the key exchange, then they're gonna fail. And because the data's been modified, Alice and Bob can look at this and go, hang on, this isn't the kind of data I was expecting. This is different kinds of data. That doesn't work. Someone's listening in on us. And so it's been like proven to be really secure. Also, there are like quantum computing isn't going to be able to solve every problem. Right now, lattice-based encryption is putting up the biggest fight. It's an encryption scheme that seems to be incredibly difficult for classical computers and also seems to be incredibly difficult for quantum algorithms. I've provided some links there too. But this is stuff to start looking into, start becoming aware of, because easily, like, we could start seeing the effects of this within our lifetime, I would say is pretty fair. We're all, like, researchers are already working on building together bigger and bigger quantum computers. They aren't really there yet. Like, right now, I think the biggest one is, like, we've chained together 17 atoms. Like, you go, good job. But this is incredibly important because people are going to be thinking about this, and you can bet, like, as soon as quantum computing hits mainstream, it becomes big enough and feasible enough to do things, then people are going to be trying to break RSA, even 4096-bit RSA. And so as computer scientists, especially anyone who's working in information security, it's absolutely crucial that we find ways to beat the system. We're in a race, basically, for can we develop incredibly secure options before the options that we've got right now, which, reminder, our options are working on the basis that, you know, prime factorization is inconvenient, right? Lifetime of the universe to solve, yeah, it's inconvenient, but not unsolvable. And so we need to find ways that are truly, truly impossible to break for quantum computing. Yeah, that's what we've got. We wanted to thank Dr. Philly from the mathematics department. He is actually the cryptography instructor. And when we realized this was something we wanted to do, we reached out to him and he was able to point us towards some resources. Yeah, do you guys have any questions for us about anything we've talked about today? Wes?
How long until I can own a quantum computer?
Well, I mean,
30 years.
lifetime of the universe.
Which if quantum computers are around, will take how long?
Not very.
Great.
Or quantum computers.
I'll hold you to that.
You what?
How would quantum computers actually even be like built?
So the idea is you're basically chaining together fundamental particles. These are really any particles that are small enough to behave quantumly. So you're chaining them together, and you can actually kind of encode information using various quantum properties, mainly spin, I think, is the big one. I don't fully understand quantum mechanics, but the idea is you can chain a bunch of properties. We like to express kind of that superposition of like multiple properties as this. This is called a block sphere or block sphere. Blocks? I don't know. But like you can see, we have these axes, but right here, psi, that's actually like the value. So it's got a degree of X-iness and a degree of Y-iness and a degree of Z-iness, but this is all encoded onto one particle. This is what people are talking about when they say like quantum computers take advantage of superposition. Because what you can then do is you can say, well, kind of this X-axis I can use to refer to like this state, right? Maybe this factor. And the Y will refer to this property, and Z will do this, right? And depending on which particle you use, I think you get like a whole bunch of different kind of properties that are just kind of room to manipulate. I think. I'm still trying to find a solid explanation of quantum computing between basically, oh, it does everything in parallel, and like research papers. I'm trying to find a happy medium. It is hard.
So the way I've always heard it is that you use a quantum computer, you calculate the correct thing, and then you use a bazillion alternate universes to calculate the wrong thing.
Yes. Yeah, basically.
Seems a bit wasteful. Whole billion of the
Not our
universes.
universe.
Hey, but it's convenient though.
It's not our
Hey,
universe.
Lifetime of the universe means like short lifetimes for other universes. We're just wasting. Yeah, trust me, it works out.
Gosh,
I
maybe
do
become
math.
a universe hippie, like save the other universes.
Universe. Yeah, universe rights. Yeah. Any other questions about anything we have talked about today?
Will I be able to Netflix on a quantum computer?
Let's throw the quick list.
I'm gonna say yeah, because I basically just use my PS4, which is a $400 machine for YouTube now. So yeah, I'm gonna say you can just downgrade it if you really want.
Okay.
I mean, there's like.
As long as Netflix is still
Yeah.
around.
So the thing is, like, this is really interesting. Like, people are like, wait, what can I actually do with a quantum computer? Chances are good. It's like quantum computers are never really gonna hit the mainstream so much. They're mostly for doing this kind of stuff. Yeah, I don't really know. You could Google it. I'm sure there's been many a diatribe across the internet about this. Yeah. Anything else? Any other questions? Well, cool. Thank you all for coming. Thank you, Sam, for helping put this together. Yeah. If you have feedback for us, please let us know. Ways we can improve, things we can do differently next time. If you need more enigmas,
Yes, we do have extra paper enigmas.
we have many a paper
You know your
enigma.
roommates are going to want to use these too. Like this is classics right here.
Yeah.
You're an enigma.
Oh, I said
that.
From now on in the ACM group, we make crypto.
Oh, God.
But we have like a key file that we all.
Did you get it working?
Yes.
Great.
Nice.
So,